Hi everyone. Today we're going to be starting talking about our second to last law for this chapter, Dalton's law of partial pressure. So thus far we've talked about Boyle, Charles, and Gay-Lussac. Then we've wrapped those three up and we put them in the combined gas law. We've added the ideal gas law for looking at one gas under one set of conditions. Now we're going to be looking at Dalton's law of partial pressure. In this law, we're going to hold the the temperature, the volume constant. We're going to only be relating the number of molecules that are in the container with the amount of pressure that they create. What this means is that Dalton is saying that each molecule directly affects the pressure of the gas. So imagine we're talking about pressure, which means we're talking about collisions. So for every collision, for every gas particle we have, we're increasing our number of collisions. The more we increase the number of collisions, the more pressure we have. So as we keep adding more pressure or more molecules, we get more pressure regardless of the type of molecule. It doesn't matter if it's an oxygen or if it's nitrogen or fluorine. If we're at the same temperature, every molecule of gas that we add adds more pressure. And so that's it, adding. This is the adding law. It's a really nice math law where we get to just add and subtract. So Dalton's law says that in a mixture of gases that is confined in a fixed volume, so it's in its own volume, volume's constant, temperature's constant, each gas provides its own partial pressure contributing to the whole. So the individual gas's pressure, the pressure due to oxygen or the pressure due to nitrogen or to fluorine, each of those is called the partial pressure. And when we look at a room and we say, okay, there's the pressure due to oxygen, to nitrogen, and to fluorine, we total those up, and that's going to give us the total pressure, which is really the basis of Dalton's law. So Dalton's law of partial pressure tells us that the total pressure of a mixture of gases is equal to the sum of the partial pressures of the component gases. So we're going to look at that definition piece by piece. Okay, so there's an example over here on the side, and I'd like you guys to follow along with it. So we're just going to get oriented to the example for a second. So we have an initial container up here. It's holding 0.5 moles of hydrogen gas. And it's in a 5-liter container, fixed volume, at 20 degrees Celsius, fixed temperature. So what you can notice about all of these is that the volume and the temperature are going to stay constant throughout the example. Okay, so we have 5 liters at 20 degrees Celsius, 5 liters at 20 degrees Celsius, 5 liters at 20 degrees Celsius. So the only things that are changing is how many moles are in the container and what pressure that exhibits. So we start out with the partial pressure for hydrogen. The partial pressure for hydrogen is 0.5 moles, creates a pressure of 2.4 atmospheres. For helium, 1.25 moles creates a pressure of 6 atmospheres. Now here's where Dalton's law comes in. If we add the two amounts of gas, the helium and the hydrogen together, if we add them together in this container, and we keep it at 5 liters and 20 degrees Celsius, we keep that constant, the total pressure is going to be equal to 8.4. So what's happening here is we have the pressure from one container, okay, the pressure from the hydrogen container is providing a pressure of 2.4 atm. And the pressure from the helium container is providing a pressure of 6.0 atm. So when we put this stuff into this container, when we combine these together, so now we have a container with helium and hydrogen, okay, both of these things together, we have a total pressure of 8.4 atm. We just add these together. So what Dalton's law is basically telling us is that the total pressure is just equal to all of the individual component pressures. This can apply to this example over here. it can apply to the atmospheric pressure. In our atmosphere, we have to add oxygen to nitrogen to carbon dioxide. All those gases together in our environment create the atmospheric pressure. So altogether, if you looked at the pressure from oxygen, from nitrogen, from carbon dioxide, you would get a total pressure of 101 kPa, or 1 atmosphere of pressure. So to get the total pressure, you take the individual pressures, the partial pressures, and you add them together. All right, so there's Dalton's law. So we have a couple of little examples here. This one's just a really simple kind of introduction to Dalton's law. So we have two separate gases. We don't even explain which one is which. We have two separate gases. Gas 1 here that has a pressure, and you can read it off the gauge, has a pressure of 1 atmosphere. And then we have another gas in here, and this gas has a pressure of 2 atmospheres. Now, when we put these together, and you can see that they were very consistent here, even the number of molecules, if you counted the number, we have 1, 2, 3, 4, 5 blue molecules, and over here, 1, 2, 3, 4, 5 blue molecules. And up here we have 5, 10 green ones, and here we have 5, 10 green ones. So we've kept exactly the same number of moles at the same temperature and the same volume. When we combine them, their pressures are 1 plus 2 gives us 3. Total pressure ends up being 3. So Dalton's law is just an addition law. Okay, so we're going to do an example problem together, and I'm going to show you how to apply Dalton's law into the 5-step method. So what we're going to do for this one is we're going to use this 5-step method that we always use: given, find, use, plug in, and solve. And we're going to be applying that to the example of Dalton's law that is listed in your notes here. So we start out with a mixture of oxygen, hydrogen, and nitrogen gas. So the way that we're going to identify these different things is we're going to call them each pressure. So if it's pressure for oxygen, I'm going to put a P with a little sub O, or O2, pressure due to oxygen gas. If you don't put the 2 there, that's okay. We have pressure due to hydrogen gas, okay, H2, and pressure due to nitrogen gas, okay. And then lastly, it tells us that the total pressure is 288 kPa. So we're going to say P total, or PT, okay, or you can write P total, is equal to 288 kPa. Okay, so we start with that. We're going to be using Dalton's law of partial pressure, but before we get there, sorry, I didn't write down the next sentence. If the partial pressure of oxygen and hydrogen are 212 kPa and 83 kPa respectively. So when they say something like that, I think you guys know this from your English classes, but when they say respectively, that means that the first one goes with the first one. So oxygen goes with 212 kPa, sorry, 112 kPa. And hydrogen goes with 83 kPa. And then it says, what is the partial pressure exerted by nitrogen? So we have all of our components here are given in our finds. We're going to be using Dalton's law of partial pressure. Anytime you see partial pressure in the question, you know you need to do a Dalton's law problem. So we're going to be saying P total is equal to pressure of oxygen plus the pressure of hydrogen plus the pressure of nitrogen. That's Dalton's law. Dalton's law says that each of these individual pressures adds up to give us a total pressure. So now we just plug in. So P total, 288 kPa, is equal to pressure from oxygen, 112 kPa, plus pressure from hydrogen, which is 83 kPa, plus the pressure from nitrogen, PN2. Okay, and so with this, now we can go ahead and plug in these, plug into our calculator. You can, I mean, I feel like I don't need to tell you how to do this, but you can subtract, you can add these together and then subtract them from the other side. I don't like to do intermediate steps like that, so I plug in 288 minus 112 minus 83, but of course you could add them together first. And what's left is PN2 is equal to 93, and the unit for that is going to be the same unit everything has been in, kPa. And if you wanted to double check it, of course you would do 93 plus 83 plus 112 to make sure you get 288 back again, and I do. So there's our answer. All right, there's Dalton's law.